Welcome to STEM education. I am Syed Wahaj, and today we are going to learn physics for the 13th year or A2 level of physics. So the topic that we are going to deal with today is energy in collision. That is what we are going to study today. We are going to study about energy in collision. Last time when we were discussing about this topic, we had an understanding about the idea of energy. We had an understanding about the idea of energy. And what was that idea all about? That idea of energy was all about energy is the currency of universe. Energy is the currency of universe. That is what the idea of energy was all about. So what do we understood by the idea of currency? For example, if there's a person A, this is the person A, and this is the person B. When A wants B to do something, then A would give some amount of energy to Mr. B. Let's say A gives $5 to B and asks B to clean his house. So B would clean his house. Any activity is going to happen only when some amount of energy is transferred, some amount of money is transferred from A to B. Similarly, in the universe, whenever some amount of energy is transferred from one body to another, then any activity happens. So the basis of any activity happening in the universe is basically dependent upon the amount of energy or the method in which the energy is being transferred from one body to another. The other thing that we had studied was the modes of energy transfer. The modes of energy transfer. Modes of energy transfer. So the modes of energy transfer are basically, there are two modes of energy transfer. One is called work. One is called work and another is called heat. So when we try to understand work, work was the amount of energy that was transferred from one body to another when some force is applied and the motion happens in the direction of force. For example, we have this ground. This is what we had studied earlier as well. We have this ground, and on this ground, we have a block, and this block has a mass M. And again, we had a body. The name of the body was A. And then this body A is pushing this block rightwards with a force of Fma. Then what happens is that under the influence of this force, this block of mass M moves a certain distance to the right. Let us assume that the displacement of this block is, let's say, 2 meters. That is called the displacement delta R of the block. So what happens if we multiply this displacement of 2 meters with the force of Fma, let's say it's 10 Newton, then it will be equal to the force, the work done by the force Fma. The work done by this force, this is equal to the force into displacement in the direction of force. Force into displacement, along the line of force, Okay. So that was the work done. If the force and displacement are in the same direction, if the force and displacement are in the same direction, if the force and displacement are in the same direction, then the work done is positive, then the work done by the force is positive, The work done by the force is positive. Also, the body on which force is applied, the body in which force is applied gains this much of energy, gains this much of energy, this much of energy. And the body which applies force loses this much of energy. The body which applies force loses energy, loses energy. So let's try to have a diagrammatic understanding of this whole situation. We have this ground. This block is of mass m. The force on this block is applied by Mr. A. So this force is known as force applied on mass m due to A, which is equal to 10 Newton. And then this block moves this much along the direction of force. Let's say it moves by 2 meters. So work done by F and A is equal to 10 into 2 equals to positive 20 joule. Positive 20 joule. So that means 20 joule of energy, 20 joule energy is lost by 20 joule of energy is lost by the body A, and 20 joule is gained by mass m. Okay. Similarly, we can say that this whole situation can also be visualized in another fashion. We can have this whole thing. If the block is moved by 2 meters, the man is also moved by 2 meters. So the man has moved in this direction, and then there's a force also acting on this man. The force acting on this man is along this direction. The force by the block on the man would be backwards. This would be the force applied on the man A due to block M. Okay. So the force would be opposite to the displacement of 2 meters, and this would be force on man A due to block B, and the value of FAB is going to be 5 meters. Okay, 5 newtons, 10 newtons. So it's going to be 10 newtons. 10 newtons. So the work done would be equal to negative of 20 joule. What does it mean? The body which applies force on A is mass m, and the one who is applying this force, if work done is negative, if work done is negative, if the work done is negative, then the body which applies force gains energy. So these were some topics that we have studied earlier, but now we are going to actually study about different types of energy. Different types of energy. Okay. So if we are going to study about different types of energy, it is going to be 2 types of energy. The first one is called kinetic energy. Kinetic energy. And the other type of energy is known as potential energy. Potential energy. Okay. So we have one kinetic energy, and the second one is the potential energy. So let's try to understand what kinetic energy is. Kinetic energy is the energy of a body due to its motion. Energy of a body by the virtue of its motion. By the virtue of its motion. By the virtue of its motion is called kinetic energy. It's called kinetic energy. Okay. So let's try to find out how much kinetic energy is for a certain body which is moving with velocity. Let's try to understand. So this is the ground, and on this ground we have a block. The block is of mass m, and a force F is being applied on it. Okay, so what will happen? This block of mass m would move by a certain distance, and it will arrive at this point, and this displacement would be known as delta r. Delta r is the displacement. And while the body would be moving, it would be having an acceleration a. So if we remember, we know that force is equal to mass into acceleration. Okay, so what the acceleration would be? It would be F upon m, right? Okay, so that would be the acceleration. What would be the initial velocity of this block? It is 0, and the final velocity would be v. Okay, so how much would be the velocity? How much would be the work done? The work done would be equal to force into displacement delta r. Okay, and what would be the value of displacement? Delta r. Delta r would be, we can apply the force. S is equal to ut plus half at squared. Half at squared. This is the formula. This is the second equation of motion that we can apply. Since the value of initial velocity is 0, we can take that delta r is equal to s. Delta r is the displacement, which would be equal to s, and that would be equal to half acceleration into t squared. So half acceleration. What will be the value of acceleration? It would be equal to F over m. F over m into t squared. Okay. Okay. So half of F over m into t squared is equal to delta r. Okay. Also, we have this equation, v squared is equal to u squared plus 2as. We have this equation. So what is the value of v squared? V squared will be the final velocity, u squared would be 0, 2 times acceleration would be F over m into displacement. S would be half of F over m into t squared. Okay. So we can write down that the work done is equal to change in kinetic energy. Work done is equal to change in kinetic energy. Change in kinetic energy. Work done is equal to change in kinetic energy. What would be the work done? Work done would be force into displacement. F into S is equal to kinetic energy KE, because KE final minus kinetic energy initial. Minus kinetic energy initial. So kinetic energy, the initial value of kinetic energy is going to be 0. So it would be kinetic energy final. So force into displacement, what would be the value of the force? Force is equal to mass into acceleration into displacement is equal to kinetic energy, right? Okay. Also, we have the value of v squared is equal to u squared plus 2as. So v squared over 2a can be written as the value of equal to s. So m into a into what would be the value of S? S would be equal to V square over 2A. So A gets cancelled out, that would be equal to kinetic energy, so kinetic energy becomes equal to half mv squared. Okay. So if a body is moving with a velocity v and it has a mass m, then its kinetic energy would be equal to half of mv squared. That's what we understand. Okay. So what is the kinetic energy of a body? Kinetic energy of a body is equal to the half of mass of a body into the square root of the velocity. Okay. This is what the kinetic energy is all about. So what we have understood now, till now, that if there's a body, and the body is on the ground, the body is on the ground, okay, the body is on the ground, it has a mass m, and it is pushed by a velocity, by a force F, it is going to move with an acceleration a, and the value of acceleration a can be written as F over m, and it moves by a distance s. So work done is equal to force into displacement. We can write force equals to mass into acceleration into s, and about the value of s, we can use the formula v squared is equal to u squared plus 2as. So in place of s, we can write v squared upon 2a. The a gets cancelled, it becomes equal to half mv squared, that is equal to the work done. And the work done would be stored in the block in the form of its kinetic energy. Why? Because once we start pushing this block, the block would start gaining the kinetic energy. And once it starts gaining the kinetic energy, the final kinetic energy that the body would be having would be equal to the amount of work done by the force F. So that's what it's all about. Now we have understood the idea of kinetic energy. What is the idea of kinetic energy? The idea of kinetic energy is that when a block is pushed, when something is pushed, and on the basis of pushing or pulling something, the speed of a body changes, then the amount of energy contained by the body in the terms of its motion, it also changes. So what would be the total energy of a body that moves with the velocity v, and it has a mass m? The amount of energy carried by that body would be equal to half of mv squared. That is known as the kinetic energy. Kinetic energy is the energy of a body by the virtue of its mass as well as the amount of motion that it is performing. So, so that's about that's basically the potential and kinetic, the idea of kinetic energy. The other thing that we are going to discuss about is another form of stored energy, and that form of stored energy is known as kinetic energy, is known as potential energy. So we are going to discuss about the idea of potential energy. We're going to discuss about the idea of potential energy. Potential energy. Okay. Potential. Okay. So let's try to understand the idea of potential energy. So the next idea that we are going to deal with is about the idea of potential energy. Now, what we have already understood about the energy. Energy is the capacity to do work. The capacity to do work. That is called energy. And it is basically the currency of universe. The currency of universe. Okay. So if somebody has the currency of energy with him, then he can do a lot of work. Like in our day-to-day life, if somebody has a lot of money, he can do a lot of things. Now, this energy is transferred in two ways. The first way of transfer of energy is by work. That is by applying force. by applying force. By applying force. So if you are going to apply force on something, and that something starts moving in the direction of force, then you do some work. And when you do some work, you lose some energy, and the thing which is being pushed by you, it gains that much of energy. The second process of energy transfer is called heat. And heat is the energy which is transferred due to temperature difference. Due to temperature difference. Got it? Due to temperature difference. Okay. Now, this is what energy is all about. Energy is the capacity to do work. After having an understanding of it, the energy is also characterized by whether it is stored, whether it is transferred, whether it is transferred, or whether it is stored. So the transferred energy can have two modes of energy transfer. One is work and another one is heat. And the stored energy is also of two kinds. The first one is known as the kinetic energy. It's known as the kinetic energy. Kinetic energy. It is energy by the virtue of motion. By the virtue of motion. And the second one is energy by the virtue of configuration. So let me tell you, what do we mean by energy by the virtue of configuration? Okay. So let's suppose that this is a tower. This is a tower. We are having this tower. And this is the ground. And let's take a ball which is placed on this ground. What we are trying to do, we are trying to apply some force on this ball upwards. And under the influence of this upward force, this ball is shifted to the top of this tower. So what happens is that we can say that the ball has moved by a distance of h. So I can tell you that the work done by this force would be equal to force multiplied by h. Now force and h both are in the same direction. Therefore, the work done would be positive. The work done would be positive. Let's say it's 100 joule. So 100 joule positive work is done by the force F. And who is applying this force F? The force F is being applied by myself. I am applying this force F. So what is happening here? That I am losing 100 joule of energy because I have done 100 joule of work. So 100 joule of energy is being lost by me. But where this 100 joule of energy is going? The 100 joule of energy is going to get transferred and stored in this ball. Now, initially, the ball was at point A, and finally, the ball was at point B. So the configuration of the ball has changed. The arrangement of the ball has changed. And earlier, the ball was arranged at the ground level, and finally, the ball is now arranged at the top of the tower. So clearly, we can say that configuration of the ball has changed. Clearly, we can say that configuration of the ball has definitely changed. Now, for the purpose of changing this configuration, we had to apply some force. And when we applied some force, then the amount of energy which was lost by the person who was exerting that force, in this case, the external agent, he loses that much of energy, and this energy is stored in the body. Now, let's take another example. Let's talk about this thing. Okay, what is this? This is a rough surface. This is a rough surface. Okay. Now, what is a rough surface? Rough surface is something that is causing a friction. Now, if I am going to apply a force F on this rough surface, this block is going to move in this direction, but it is being held back by the friction force, Okay, so this friction force is trying to stop the block from moving. So the block has a mass m, and this block is trying to move rightwards, but this friction is trying to stop this block. Okay, but it is trying to stop this block. Okay. It is trying to stop this block. Okay, so we can compare this case with the case when we are trying to lift the ball. When we're trying to lift the ball, this ball, while it was in the middle of the air, this ball was being lifted upwards by a force F, while also it was being pulled downwards with a force of mg. So this force is being stopped by the gravitational force. The force due to gravity, the Earth's gravitational pull, is trying to stop this ball from going to the top of the tower. As opposed to this mg force, here we have a friction force, and this friction force is trying to stop this block from moving over this rough surface. So clearly in both these cases, we can see that the external agent is applying force on a body, and another force is trying to stop the external agent from being capable of moving that body. In the first case, the force which is trying to stop the external agent is the mg force. And in the second case, when we are trying to slide something over a rough surface, the force which is trying to stop this external agent from moving the block on the rough surface, that force is known as friction. So in the first case, gravitational forces are stopping the block, stopping the ball, and in the second case, friction is stopping the ball. But there is a basic difference between the gravitational force and the friction force. While the gravitational force tries to stop the ball from going upwards, it doesn't create any heat. The body, while it moves upwards, it doesn't get hot. It doesn't become hot. Okay. But when we're talking about friction, when the block is rubbing the floor and moving on the floor while sliding, what happens is that the surface of the block, which is in contact with the rough surface, that surface becomes hot. Okay. So what happens when the surface becomes hot? When the surface becomes hot, it leads to the loss of energy. Okay. So in the second case, when we are talking about friction, the energy lost by the external agent, the work done by the external agent equals energy lost by external agent, energy lost by external agent, lost by external agent, by external agent. Okay, but here the work done by external agent equals to energy lost by external agent, and this energy lost by the external agent, it gets dissipated in the form of heat. It gets dissipated in the form of heat. Correct? So the energy lost by external agent doesn't get stored in the block. So it doesn't get stored, it gets dissipated. Or in other words, we can say that the energy does not does not get stored. The energy does not get stored. Okay? But when we talk about this thing, when we talk about the external agent doing some kind of work against the gravitational force, here the energy gets stored and it does not get dissipated. Here, the energy gets stored, and it does not get dissipated in the form of heat. Okay. Well, when we, after discussing this concept, we can arrive at a conclusion. We can arrive at a conclusion that forces are of two types. Forces are of two types. Okay. The one type of force is the kind of force if we work against that force, okay, like gravitational force. If we work against that force, no heat is produced. If we work against this force, no heat gets produced. No heat gets produced. Okay. And then there's another kind of force, if we work against such forces, if we work against this force, some heat is produced. Heat is produced. Okay. So this is where, if we work against this force, no heat gets produced, and this is where the heat produced. So no heat produced, like gravitational force, Okay. Gravitational force, also spring force. And here, like viscous force, or friction force. Okay. So gravitational force and spring force, if we are going to work against the gravitation, if we are going to press, to apply force and try to compress a spring, then we would have to apply some force while trying to compress that spring. But while the spring gets compressed, its energy, it does not start producing heat. Okay. So such kind of forces are known as conservative forces. Okay. And such kind of forces are known as non-conservative forces. Okay. So how would you know that whether some force is conservative or non-conservative? What we are going to do, we are going to apply an external force which would be opposite this given force, and if the heat is produced while the work is being done, then such is a non-conservative force. But for example, on somebody, if there's conservative force only, if there's no heat produced, then this is called a non-conservative force, and this does not create any kind of heat. So let's write it down. I would suggest you to write down the difference between these two kinds of forces, like conservative and non-conservative forces, right? I would suggest you to write that down. Okay, I guess you've written it down. So now we have understood there are two types of forces. One is conservative force and another is non-conservative force. What happens with a conservative force? When we are talking about a conservative force, this whenever somebody works against a conservative force, no heat is produced, no heat is dissipated. And when we are working with these non-conservative forces like that friction or viscous force, heat is getting dissipated. So what happens here? Whenever work is done against a conservative force, the amount of energy lost by the external agent, it gets stored in the system. It gets stored in the system. Okay. So whenever external agent, the external agent does some work against a conservative force, then the amount of work done is equal to the amount of work done is equal to the amount of energy lost by, so whenever a conservative force was lost by the external agent, gets stored in the system. It's stored in the system. Okay, in the form of potential energy. In the form of potential. Go ahead, write it down. Go ahead, write this thing down. This whole thing is actually the definition of potential energy. Potential energy. Now that we have understood the idea of potential energy, we can understand something known as conservation of energy, conservation of mechanical energy, conservation of mechanical energy, mechanical energy. What do we mean by conservation of mechanical energy? Conservation of mechanical energy, it means that if there's a body and we find out its kinetic energy and we find out its potential energy and we add them up, this is known as the mechanical energy, right? Kinetic energy plus potential energy equals mechanical energy. Okay, kinetic energy plus potential energy, that makes up the mechanical energy. Okay. Now, if there is no non-conservative force, if there is no non-conservative force, then no energy will be lost. No energy will be lost. And net kinetic and potential energy, net kinetic and potential energy, would be conserved. Okay. So if there's no dissipation of energy, if there is not at all any dissipation of energy, then the whole of kinetic and potential energy summed together would be constant. Sometimes it might happen that kinetic energy would decrease, but an equal amount of potential energy would increase. I'll give you an example of it. Just write it down. Just write down the idea of conservation of mechanical energy first. Go ahead and write. Okay. Okay. So we have understood the idea of conservation of mechanical energy. Now let's take an example. When mechanical energy is conserved. When mechanical energy is conserved. Mechanical energy is conserved. So let's take a pendulum. Here we have a pendulum. We are having a pendulum. Okay? This is a pendulum that we are having, and this pendulum is somehow it is hanging from the ceiling, and we give it a push to this side, we give it a push to this side. So we are having this pendulum and we're trying to push it to this side. So it goes like this. And so this pendulum would move like this. This pendulum would move like this. Okay. So it goes rightwards, then come back to this original position, then goes leftwards, and then come back to its original position. So this is what it's going to happen. It's going to go to and fro. It's going to move to and fro. So to and fro motion of this pendulum would cause what? No energy would be lost. No energy would be lost. Okay, no energy would be lost, and no heat would be produced. No heat is going to be produced. It's going to be produced. No heat is going to be produced when it oscillates. When the pendulum oscillates. When the pendulum oscillates. When the pendulum oscillates. Okay. No heat is going to be produced. So when the heat is going to be produced, the heat is going to be produced when the pendulum is undergoing its oscillation in an environment where there is air and there's a kind of air friction. But if there is no air friction, let's suppose that the pendulum is making to and fro oscillatory motion in vacuum, then no heat will be produced and the total mechanical energy would be conserved. So at this point A, B, and C, the B point is the neutral position. The B point is the neutral position. Is the neutral position. Is the neutral position. And A point and C point, C and A are the extreme position. Are the extreme position. So at the extreme positions, at both point A and point C, the net energy would be, the net motion would be zero. So the potential energy at point A and point C would be maximum. Potential energy at point A and C, at point A and C will be maximum. And at point B, it will be minimum. It will be minimum. Okay, it will be minimum. And at point B, at the lowest position, at point B, the speed will be maximum. The speed will be maximum. And kinetic energy will be maximum as well. Go ahead, you can write it down. This is a very important example. And the total mechanical energy is going to be conserved. Because when the kinetic energy is zero, the whole of the energy would be in the form of potential energy. And when the potential energy would be zero at point B, the whole of energy would be in the form of kinetic energy, the energy due to motion. Okay, so go ahead and write it down. So I guess today we have studied about the energy and how in the different forms the energy gets stored, and the kinetic energy, potential energy, and the conservation of mechanical energy. These kind of things are going to be applied when two bodies are going to collide with one another. When they collide, sometimes there is a loud sound of collision. When person one is going to collide with person second, there is a loud thud when they are colliding with one another. But in some other cases, it doesn't happen like that. It doesn't make a lot of noise. All the energy is conserved. So these are the two types of collision, and what are the energy considerations that we are going to study about in the next topic, when we are going to start about the energy considerations when collision happens. So I thank you so much for joining today. And today we are going to end our class, and we'll get started with the topic where we have left today at the next session. Thank you so much, and goodbye for today. Let's meet in the next class.